have a look into debris flow mitigation. Debris flows pose a very, very high risk to people and infrastructure. Also here in Switzerland, in this presentation, I don't have proper pictures from Switzerland, but I can assure you we have debris flows here also quite frequently and with quite a huge impact on infrastructure. Although our rainfalls cannot be compared with the rainfalls in Southeast Asia, but nevertheless. So let us have a look or let us quickly look into the process or into mechanism, because at one point you will understand rockfall and debris flow, even though we both mitigate by barriers, are not the same process and do have different characteristics, especially when it comes to the dimensioning. So if we look here, the displacement characteristics of debris flows, we have, of course, water involved, whereas usually in rockfall or rock slides, we don't have, but we can have as a triggering mechanism. But the rock fall itself will be like a dry mechanism. That one we can skip. So the decisive factor for debris flows, of course, that we have some loose debris or materials that can be mobilized. We have water and rainfall. We need to have a certain inclination also, of course, which then eventually results into debris flow. And we have a look here into, excuse me. These videos here, both from the same site. We are very lucky. We found a site here in Switzerland, actually, which is a beautiful test laboratory in nature, because they experience like 10 to 12 debris flows a year. So the research institutes of WSL and SLF, and also we have been doing quite a lot of installation and testing there because of this environment. And what I want to point out, what you see already, is the different characteristics here. Huh? On the left-hand side, you see something like more like a mud flow. This will result in a higher velocity, but in lower densities. Whereas on the right-hand side, we can see a more granular flow, bringing more coarse material with it, with higher densities, but usually slower front velocities. And this is the very same. This is not exactly the same location, but it's on the very same channel. That we can find these different kind of appearances of debris flows. So, as the summary for the debris flow characteristics, these are input parameters which can help a lot to dimension the system in a way that the next event can be mitigated. So inclination, for example, is something which is relatively easy to determine, of course, from the sites. But the characteristics or the type of materials being carried in the flow, and also the volume, is something that very often it's quite hard to determine. And very often, if there is a documentation of historical or past events, that these can help a lot to get a better idea of these parameters. So for us in GeoBook, it was a little bit the same. Like it went with the avalanche protection structure, which I showed you in the very beginning, and people recognized, there are rocks in it, and then developed rockfall barriers. And in the early 2000 years, we had a couple of incidents where actually rockfall barriers have been stopping debris flow events. So actually, that's from where we took it then to say, okay, this is a rockfall barrier and it's not located in a channel, but still it experienced a debris flow and could mitigate it. So let's look into it. If we can come up with a more adequate solution, actually. And this is here on the right-hand side, you can see how we have done it. We did some laboratory tests. We did then eventually in this channel, which you have seen before with this mud and granular flow, we did not only one, we did in the end a couple of test installations. These structures have then also be equipped with the strain gauges and measuring devices on the deformation and loads in the structure itself, which we then took into numerical modeling to get a better understanding of these processes, and eventually also then come up with a designing software to determine what kind of energy level we require to determine the the very energy in the events. And if you look here on the right hand side, there's two different load concepts which is behind the designing, because first we have the stopping and filling of a barrier, and then very often depends a little bit what you want to do. We won't recommend to clean it afterwards, but then you have overtopping events. So this is what is here called overflowing. And this is a total different load experience for the structure. So we have to take into account these different load models on the debris flow dimensioning. And to illustrate again a little bit the difference between rockfall and debris flow is really that in rockfall we have a dynamic, very often singular event on a specific location of the barrier, whereas in a debris flow we receive an area load in the barrier. So it's more like a pressure model what is behind it rather than an impact energy model. So after this a little bit of theoretical background, I just take you now again to a couple of projects. This is one of the test installation in this Ilgraben, this natural laboratory which we have been finding here luckily in Switzerland, and a couple of other installations. This is a very special project adapted installation of a debris flow barrier with the retentioning volume of 30,000 cubic, but it's not a standard system. It was quite some work to come up with the design and also in the execution. So the height here is something like 15 meters, and one installation here in Canada, but we look more into detailed projects now. I forgot about that. Yeah, for the structures itself, in like V-shaped valleys, usually these mitigation structures can come along without any posts. In more like U-shaped channels, then we would find posts in the structure, like in the rockfall barriers. So I have two small pictures here of this Vaishnu Devi project again, where also you can see here is the pilgrim path with this rock metal shed roof, where we also installed two debris flow barriers in these channels. This is the second one. You can see here, this is the pilgrimage path. And now have a quick look at the project in Vietnam. So this is electricity power station. We can see here they have a channel. This is this channel, which we can see here. But during a bigger event, actually most of the debris here went over that wall and flooded the whole area. You can see here the excavator still removing the debris. And we came up with a rather unusual geometry for this barrier, but this was due to requests and the demand of the project boundary conditions at that time. And we can see here one of the preliminary locations actually indicated in the very first, very early in the project history. So you can see here that shotcrete area, which is the same, which you can see here on the left-hand side picture with the ready installed barrier now in Vietnam. Any questions? No? Okay. Then I will show you, I want to show you this project in the Philippines. Although we did quite a lot slope stabilization here, we also put debris flow barriers. So the situation is that they have a major road down here. They have a retaining wall, 300 meters long and 6 meter high, with something retaining capacity of 20,000 something cubic. And the first time they brought me here, or I went there, we were standing here at the exit of this gorge. This is maybe 5 meter wide and 10 meter high, almost vertical walls. And everybody was looking at me and asking me, so what is the solution? And I was like, okay, guys, let's try to find a way up here to see actually where all this material is coming from, because I can't possibly come up with some solution or idea of a solution if we don't understand what actually is happening on the top. So this is how we can see here on the right hand side. You can see this retaining wall, and during typhoon season this retention volume was not enough and the road was flooded and blocked, and they experienced traffic jams up to 50 kilometer, and it's quite an important road in northern Luzon to connect Manila with the northwestern part of Luzon. So they were eager to find a solution. And this is one of the very early drone pictures which we did at that time. So here on the left-hand side is the road and the retaining wall. And you see here the materials deposited behind that wall. And this actually is the gorge, which I've been mentioning earlier. And up there we can see, okay, something is happening. We went there the very first time by foot. Well, also in the next 2 years, we went there a couple of times. It takes like almost 2 hours, quite steep. And the first time we arrived up there, it just started to rain. And we were like a party of 12, 15 people. And when we arrived there, it started to rain. And after 10 minutes was clear, okay, we have to get down as fast as possible, because it's not, it's quite challenging going up, but going down in the rain is dangerous. So the first time I was there, I had maybe 10 minutes on the side to get the first idea. And you can see here this channel where we later on see pictures of the installation or ongoing works. That one usually is dry, more or less. And it filled up in the 20 minutes when I could see it last before we went down. It filled up to 2 meters height and probably more afterwards. And this is then the main source of the debris, which we found down on the street. And this is how the slopes looked like around. So during a process of several years, actually, Then we have been coming up with different designs. The main supply of debris actually came from these flanks here, but we had here a major sliding body. You might have seen in the first picture the scar here on the scars on the top, indicating that it's also a global stability problem here. And luckily, after 3 years, we have been awarded, or well, the DPWH, the Department of Public Work and Highways, has been decided, okay, with this design version we are going to go, and project has been tendered, and we have been able to supply there almost 40,000 square meters of slope stabilization, plus 3 debris flow barrier in this channel, because we wanted to avoid that this channel gets deeper and deeper, and then even though we have been stabilizing the slopes, would then at one point affect the slope again. So this is one picture of the early days of the installation. At that point, the debris flow barriers have not been put there. And this is a picture actually more or less after the completion. I believe there is still one phase missing here in that picture, but ever since we started there in 2017, so in the last 5 years, there have not been any traffic jam or any blockage of the road, which you have seen earlier in the earlier pictures. So slope stabilization on the flanks, plus here these 3 debris flow barriers to stop deeper eroding of this channel. Some pictures during the installation, erecting the posts, then adding the mesh panels or net panels. Some more of these impressions. And then, of course, very quickly, we started to have a filling up of those barriers. This is the construction site manager here, and you can see, during normal times, there will only be a very small amount of water penetrating these fill-up sediments and going down the way, and we retain the material to prevent further erosion uphill. So I hope you had got some idea here of what we have done there in the Philippines. And this is the one project which is not from your region, but I believe is a very nice showcase of debris flow mitigation in South America, in Peru. So you can find here this Chosica village east of Lima. And we can see here that from time to time, this municipality suffered severely from debris flow events. I have a short video here. Where there was some small debris flow, and now we can see here's more to come. So this is to give you an impression of, what these people or this municipality was suffering from. And now, I mean, it gets to a point you just have to run. And in the next picture, in the next slide, we can actually then see that this is not the only location where this municipality has a debris flow problem. I think we can go to the next slide. But yeah, we have been, or it was relatively easy to come up with like this kind of risk or hazard map, and we could see, okay, there's several channels ending up here in the municipality being in the valley ground. endangering the infrastructure and the people, of course, in that area. In that community, with the help of ANA, which is the National Water Irrigation Agency in Peru, we have been then identifying these 9 creeks. We have been able to install there 22 barriers within 2.5 months, which is quite a challenge, I believe, to mitigate the risk. And you could see here in that picture, there have been like old concrete check dam solutions actually to try to prevent incidents like we have seen in the video, but they have been washed away. So again, installation in a challenging environment. So materials had to be carried or brought in by mule. Luckily, with this lightweight drilling rigs, this is not so bad actually to bring them there. The rig would be something like 120 kg, so that can be handled. And then eventually came up with the installation of these 22 barriers. This is the widest one with, I believe, almost 60 meters. Looking up into here on this old, partly or fully destroyed structures, and having some debris flow installations on top. And then only in the year afterwards, there was again a major event. And luckily, our design and the systems have been working. And you can see here, there was still some materials arriving in the municipality. Of course, the water did, but the energy and the destructive force of this debris flow can be significantly reduced if you get rid of all this material, which was then retained in the barriers.